Now in this today's video lecture, we will be talking about quantum mechanical model of atom, or we also call it as wave mechanical model of atom. Because why wave mechanical? Because it includes the wave nature of electron as well, which was not included by earlier model of atoms, right? Because it didn't consider the dual behavior of electrons, right? So first, before we go ahead and deep dive in quantum mechanical model, let's see what was the requirement for quantum mechanical model, right, based on the failure of Bohr's model of atom. Because before this we have Bohr's model of atom, which was not successful, right? Bohr's model. As per the Bohr's model, there were two major drawbacks. First was it did not include the dual nature of electron, right? And the second was it contradicted Heisenberg's uncertainty principle. Heisenberg uncertainty principle, right? Now we need a new theory or a new model of atom that should not be contradicting the Heisenberg's uncertainty principle, and it will include the dual nature of electrons, right? So the new model of atom would be quantum mechanical model of atom. Why we say it quantum mechanical? Because this model of atom is based on quantum mechanics, right? So before we understand what is quantum mechanics, let's just understand classical mechanics, right? Classical mechanics, the mechanics that we have been doing in physics, right, that is based on Newton laws of motion, right? That is your classical mechanics. And classical mechanics deals with the macroscopic objects, right? The Newton laws of motion can be applied to macroscopic objects that have significant mass, right? The rolling stone or the falling body or the planets that are moving around the sun, right? All these are macroscopic big objects, right? And they follow, or they can be studied via Newton laws of motion, right? But when we talk about microscopic objects, the small objects that have extremely small mass like electrons, right, there the Newton laws of motion cannot be applied. That means the classical mechanics cannot be applied to microscopic objects. Why? Because these microscopic objects have significant wave character, right? So we have to include their wave character as well, and the science that includes the wave character of microscopic particles, right, is your quantum mechanics. So in quantum mechanics, we would be dealing with particle nature as well as the wave nature of microscopic particles, and it tells us, or it tells us about the laws of motion of microscopic particles, right? Like classical mechanics, in classical mechanics, Newton laws of motion tells us about the motion of macroscopic particles. Similarly, in quantum mechanics, we would be studying about the laws of motion that applies to microscopic particles, right? Why we have a different science for the motion of for microscopic particles? Because if you remember the formula, the de Broglie relation, H upon mv, this is momentum, right, where wavelength was inversely related to mass, right? For microscopic particles, this value of m is extremely small, right? So their wavelength is quite significant, right? So their wave nature is significant due to high value of wavelength lambda. Whereas if we talk about macroscopic objects that we study in classical mechanics, there this mass, the value of mass is high, right? So their wavelength is very less. When we say wavelength is very less, that means their wave character is very less. It's not detectable, right? So we say that the waves, since we say that for macroscopic objects mass is high, so their wavelength or lambda is very less. When we say wavelength is very less, that means their wave character is not detectable. So we say that waves associated with particles of higher mass or macroscopic objects are not detectable, right? Whereas waves associated with microscopic objects are detectable due to their extremely small mass, right? So this relation is important to understand this concept, right, of quantum mechanics and classical mechanics, right? So now we have the science of quantum mechanics that deals with the motion of microscopic objects, right? And we know that electrons have small, the microscopic subatomic particle, the atom has a microscopic subatomic particle electron that is revolving around the nucleus, right? So we would be applying quantum mechanics to this revolving electron, and then we'll deduce the structure of atom based on our quantum mechanics, right? So when we talk about quantum mechanics, now we know that quantum mechanics is applied to microscopic objects, right? And it specifies the laws of motion, right, that these microscopic objects follow, right? So quantum mechanics was developed by Werner Heisenberg and Erwin Schrodinger, right? This was developed by two scientists. This science was developed by two scientists, Erwin Schrodinger and Heisenberg, right? Werner Heisenberg in 1926, right? However, we would be in quantum mechanics. If you talk about quantum mechanics is altogether a wider subject, right, that you would be studying in your higher classes when you do graduation. In BSc, you have this quantum chemistry, quantum physics as a separate subject. There are wider subjects, right? But here we would be introducing you to quantum mechanics, right? And we would be dealing only with the wave motion or the wave character of quantum mechanics, right? We would be applying quantum mechanics only to the study of waves that are associated with microscopic object electrons, right? So in quantum mechanics, we have a basic equation. Since the quantum mechanics was developed by Erwin Schrodinger, so the equation is based on his name. We call it a Schrodinger wave equation, right? And this equation, we would just be looking at this equation. It tells us about the three-dimensional motion of an object. In our case, it would be talking about the three-dimensional motion of electrons, right? And the derivation and the details, rest of the details as applied to other objects. How can this equation be applied to other objects, or the concept of quantum mechanics to other objects? We would not be dealing here. It would be in your higher classes, right? So Schrodinger equation, this is, we call it as the heart of quantum mechanics. The quantum mechanics, everywhere in quantum mechanics you will find this equation. The equation is del square psi upon del x square, del square psi upon del y square, del square psi upon del z square, right? Plus it's 8 pi square m h square, right? It's 8 pi square m upon h square. E is your energy, V is your potential energy, right? Psi is equals to 0, right? This is a three-dimensional equation. It tells you the three-dimensional, in our case it tells us the three-dimensional motion of an electron, which is a microscopic particles, since we are only dealing with microscopic particles in quantum mechanics. 3D motion of an electron around the nucleus, right? And the basic quantum mechanics, the basic Schrodinger equation, the way we write is h, we put a small cap on h psi is equals to E psi, right? This is the basic quantum mechanics equation, right? And what we would be doing is, this h is your Hamiltonian operator, right? And psi is your wave function, right? And E is your total energy of the system, right? And this total energy, when we talk about atom, total energy is the attraction between the electrons and the nucleus, and the repulsion between nuclei and the electrons, right? That includes the total energy of the system. So this operator Hamiltonian, right? This is an operator which operates on the wave function psi, right? Later you will see that this is a wave function whose value depends on the coordinate axis, x, y and z axis, right? So this Hamiltonian operates on the wave function psi, right? And it gives you the energy E. So this equation will give you a way, right, of constructing a way to find this Hamiltonian operator from the total energy of the system E, right? As I said, this includes, in case of electrons moving around the nucleus, it includes total attraction between electrons and the nucleus, repulsion between nuclei and the electrons separately, right? So this is important. This is the basic equation of Scrodinger. This is the basic Scrodinger equation. And as I said, that constructing the operator from the expression for the total energy of the system. This operator Hamiltonian, right, is constructed from the total energy of the system, right, like we have already discussed. Now this Hamiltonian equation is solved. Whenever you solve this Hamiltonian equation for any system, right, besides the electrons or the atom, you solve this equation to find the value of E, energy, and psi, the wave function, right? So Scrodinger equation is solved for E and psi, right? And this Scrodinger equation includes the dual character of electrons or the dual character of objects, right? It includes the wave character as well as your particle character of any object. So whichever object Scrodinger equation is applied, it applies or it includes the wave character and the particle character, right? So it includes wave character and particle character, right? So this is important, right? So now, since I said the Scrodinger equation would be solved for E and psi, right? Now what we would be doing in wave mechanical or quantum mechanical model, we would be applying Scrodinger equation. We would be applying Scrodinger equation to your structure of atom. Let's talk about, we are applying it to the hydrogen atom, right? We will apply Scrodinger equation to hydrogen atom, and then we will see how it helps to deduce the structure of atom, right? So when we will apply Scrodinger equation to a simple hydrogen atom that has one electron only, so what we are basically doing is we would be solving Scrodinger equation H psi is equals to E psi for this system of hydrogen atom that has one electron which is revolving around the nucleus, right? So we would not be solving it because this is not in the scope of class 11th, I'm sorry. So we would be solving this Scrodinger equation for system of hydrogen atom, and we will find the value of E and psi, right? Now let's see how from the value of E and psi we will deduce or talk about the structure of atom. What information does it give us about the structure of atom? This we would be looking into, right? If we talk about E, right, the value of E or the energy that we will get, right, after applying Scrodinger equation to the structure of atom, it gives us the various energy levels or energy states that we say, right? And we know that electrons, or I'm sorry, the atoms has various energy levels where electrons are moving, right? And when we solve it for psi, psi is a wave function, right, which is associated with each energy level, right? And this psi, right, have all the information of about the electron which is moving in that energy level, right? This psi is your wave function associated with energy level E, right? And its value depends on the coordinate axis, x, y, z coordinate axis, right? And later in a moment we will see that this psi is nothing but the orbital, right? We know what is orbital. It's inside orbital that we have electrons, right? And it has all the information about the electrons. It has all the information about the electrons, right? Later we will see that the energy and the psi, right, is given by three quantum numbers n, l and m. N is your principal quantum number, L is your azimuthal quantum number, M is your magnetic quantum number, right? These three are from the values of energy and psi, right? So this is very important. When you apply Scrodinger equation to the simple atom hydrogen, right, it gives you, so whenever we apply Scrodinger equation to any atom, we solve Scrodinger equation for E and psi, right? So when we solve hydrogen atom for E and psi, we will see what information or what points or what information it can give us for the structure of atom. The value of E will tell us about the various energy levels or various energy states in an atom, and this psi, which is a wave function associated with each energy, which associated with these energy levels, right? And the value of psi depends on the coordinate axis x, y and z, and the most important is it has all the information of the electron, right? And later you will see that this psi is nothing but your orbital, right? So this is really important concept, right? So psi gives you the information regarding your electron that are present in the energy levels, right? So now let's just talk a little more about this psi, right? If you remember, you have studied about sound waves and light waves in your physics, right? In physics you have studied about sound and light waves. So when we talk about sound waves, right, if this is the wave, right, so this is the amplitude, right? This is the amplitude A of this wave. So if you do the square of amplitude, this you will do in physics, what you get is the intensity of this wave, intensity of wave at any point, right? So square of amplitude will tell you about the intensity of light in case of light wave or intensity of sound in case of sound waves, right? Similarly, the psi that you have here, the value of psi, this psi is, since we are dealing with quantum mechanics includes the wave nature of electrons. So the electrons that are revolving around the nucleus is nothing but these electrons are waves, right? So this is the wave. What this psi is, psi can be taken as the amplitude, right? Psi can be taken as the amplitude of this electron wave, right? So if you do the square of the magnitude of this value of this psi, the square of psi will give you, since this is sound wave, so square of this amplitude sound wave gave you the intensity of sound, and if it is a light wave, it gave you the intensity of light. So now this is an electron wave, So it will give you the intensity of electron, right? So this psi will give you the intensity, it gives you the intensity of electron at any point. If you find the intensity of if you find the value of psi square at any point, it gives you information about the intensity of electron. When we say the intensity of electron, it means the density of electron. It tells you about the density of electron. So what it means basically is the intensity of density of electron means the probability of finding an electron at that point, right? So this psi square in a way, it means when you talk about the intensity or density of electron at any point, right, of this wave, of this electron wave, it tells you about the probability of finding electron, right, at that point. Right. So now suppose this is your nucleus, right? This is your nucleus and this is your hydrogen atom, right? And this is an electron moving, right? If I know the value of psi, right, this value of psi, from this value of psi I can find the electron density or the probability of finding an electron at any point, right? Suppose I find this value of psi square at various points around the nucleus, right? If I find the value of this psi at various points around the nucleus, right, what I get is like this. Maybe the intensity of electron density, right, or the probability of finding an electron at different points would be different, right? At some points it would be high and at some points it would be less, right? But it would never be zero, right? So value of psi square would never be zero, right? There is always some probability of finding the electron even at far away from, even at far distance from the nucleus. So you will get this kind of an electron cloud which is thicker, it has a lot of dots, here at the center, and it fades, or these dots lessens as we move away from the nucleus, right? So these dots represents your electron density or your probability of finding electron, right? This is the most important information that we get from psi. What we call to this cloud, to this circle kind of thing that is constructed using this value of psi square, we call it as electron cloud. Electron cloud, right? And this electron cloud is where you have the probability or the maximum probability of finding an electron around the nucleus, right? This electron cloud, in this electron cloud, right, we have the probability, the maximum probability of finding an electron, right? And the probability is found using this psi square. So what do you call to this electron cloud? This electron cloud is called as orbital, right? Where you have the maximum probability of finding an electron. The electron is found in an orbital, right? That is why I said initially that psi is nothing but it's orbital, right? So I'll just quickly repeat. This is an electron wave, right? The value of psi that we found from the Scrodinger equation gives you the amplitude of this electron wave. So if you find the square of this amplitude, what you get is the intensity of electron, right? Or the density of electron at that point. So when you find what this psi square represents, the probability, intensity of finding an electron means the probability of finding an electron at that point. So when you find this intensity, right, of finding an electron at various points around the nucleus, what you get is this electron cloud, right? So in this electron cloud, you have the maximum probability of finding an electron. So you call it an orbital, right? You call this electron cloud as orbital, where you have the maximum probability of finding an electron. So this orbital is, this psi is nothing but an orbital, right? So now let's see how is it solved, the Bohr's contradictions. it talked about the contradiction of Heisenberg's uncertainty principle, because in Bohr's model we defined these paths, that electrons are moving in these well-defined orbits, right? Electrons are moving in these well-defined orbits. That means they are moving in the well-defined orbits. That means we have specified the position as well as the velocity, right? When we specify the position and the velocity, then only we can talk about the definite path, right? So since we are specifying position and velocity, as per Heisenberg uncertainty principle, we cannot find the position and velocity. So this concept of orbit has contradicted the Heisenberg's uncertainty principle, right? But in case of how this problem got solved, in case of quantum mechanics, we have used the value of psi, because in quantum mechanics we solve Scrodinger equation for E and psi. So here the value of psi gave you the concept of orbital, like I explained here. So the concept of orbital does not talk about the definite path, it talks about the probability of finding an electron, right? So we are not talking about the definite path, we are not talking about the definite position of electron around the nucleus, we are just saying that there is probability of finding an electron at certain points, right? So we are talking about probability of finding electron, right, around the nucleus, right, which is given by the value of psi. When we solve the value of psi for any atom, it gives us the probability of finding an electron around the atom. And this dual nature of matter, we have already discussed that quantum